Hi everyone. So in this video, I'm going to go over a few more examples of more applied examples that go over the second derivative test and help us figure out maximum and minimum points. So let me get started. Okay. So we're given a short-run production function that is given by this particular function. Q is equal to 6L square minus 0.2L cube, where L denotes the number of workers. Now, we're asked to find the size of the workforce that maximizes Q. So we're asked to find L that gives us a maximum value for Q. So remember our discussions about maximum and minimum points using just X and Y. Now, if X star comma Y star is a critical point, then if it's a critical point and if it happens to be a maximum point at X star, the function reaches its maximum value. So that is that's how you would read or interpret a particular critical point. Here, we're asked to find L such that Q is maximized or Q is at a maximum. And to do this, so think of Q as Y and L is your X. So you have to find the value of X that maximizes Y. So here you have to find L that maximizes Q. But the rest of the process is all the same. It's just that the particular notation or the variable names that we use are going to be a little bit different. Let's go ahead and solve this. So we want to maximize Q, and that's the expression that's given here. Now the first step is to find dq by dl and equate this to 0 to find the critical point. So dq by dl is going to be 12L minus 0.6L square. And if that is 0, so let's factor out L here. So this will be L. So L into 12 minus 0.6L is 0. And that tells us L is either 0 or L is where 12, so either this L is 0 or you have 12 minus 0.6L is equal to 0, 12 equals 0.6L, therefore L is going to be 20. So I have these two values. And you can go ahead and actually compute the coordinates of Q as well if you want to get the two coordinates of the critical points. And I'm going to leave it for you as an exercise. The next step here is to find the second derivative and evaluate the second derivative at each of these two L values. So let's get the second derivative. And the second derivative is just d square Q by dl square. And what was that going to be? It's going to be 12 minus 1.2L. Now let me evaluate the second derivative at L is equal to 0. When L is 0, d square Q by dl square is actually 12 minus 0. And that's going to be 12 and it's greater than 0. If the second derivative is positive, you're dealing with a minimum point. Now let's look at the second derivative at L is equal to 20. At L equals 20, my d square Q by dl square is what? 12 minus 1.2 times 20. This is 12 minus, I think this will be what? This will be 24. So you have minus 12 less than 0. Therefore, if the second derivative is negative, we know that we're talking about a maximum. Therefore, the size of the workforce that maximizes Q is this. L is equal to 20. That's the answer. And now you can actually think about it from an economic standpoint, right? If your workforce is 0 or workforce is 20, you know that when L is going to be just 0, you're not producing any output at all. So you can kind of guess that that's going to be a minimum. And so you're only moving towards and it's good to check if that's the case using calculus. And L is 20 is definitely telling you that your output is going to be positive when you have some labor coming in. So that's another way to intuitively check if you're heading in the right direction. So that's how you solve the first part of this problem. So the second part of the question asks us to find the size of the workforce that maximizes APL. And then we are asked to find APL and MPL at this value, and what do we see? So let's take it one step at a time. Now, APL is actually the average product of labor. And it is just actually the output per unit of labor. That is what it is. That is what your APL is. Now, therefore, if it's output per unit of labor, we know APL is actually just Q by L. So let's write down the APL function. APL is now going to be 6L square minus 0.2 L cube by L. And that is just 6L minus 0.2 L squared. Now we want to find the value of L that maximizes this APL. So to do that, we first take the derivative of APL with respect to L. And we set that equal to 0. And this is just going to be 6 minus 0.4 L is 0. Therefore, 6 is equal to 0.4 L. So L will be 6 by 0.4. And this is equivalent to just 60 by 4. And you can say L is 15. Now let's go ahead and do the second derivative test to check if L is equal to 15 actually maximizes average product of labor. So let's just do the second derivative, which is d square of APL by dl square. And what is that? It's actually just minus 0.4. And that is always lesser than 0, regardless of the value of L. So we're dealing with a concave function. Therefore, we can be certain that L is equal to 15 maximizes APL. And if you want to find the corresponding APL at L is equal to 15, all you have to do is just plug in L is equal to 15 into the expression for APL, and you'll get the answer. Now, the question also asks us to calculate APL and MPL at this particular value of N, and what do you see? I'm going to leave it as an exercise for you to figure out what's going on there. And all I will tell you is that MPL is just dq by dl. So the rest of that problem is an exercise for you to finish. Okay, let's go ahead and check out the second problem. So we're given a demand equation of a good, and that's P plus Q is equal to 30. And we're also given the cost function by SPC. Now we want to find the value of Q that maximizes TR. That's the first part of the problem. TR here is total revenue. And the second part of the question asks us to find Q that maximizes total profits. Now let's do the first part of the question. I'm actually going to take another page here and make life easy for all of us. So let me just remove this to the next page. Oops. Sorry for that confusion. So we're back to the problem. So let's find Q that maximizes total revenue. And to do that, let's first write down the total revenue function. Now, total revenue, we know, is price times quantity. And we're given that the demand function is P plus Q is equal to 30. So therefore, can we write P as a function of Q? Yes, we can do it as 30 minus Q. Therefore, P times Q is now just 30 minus Q times Q. So my total revenue function is 30Q minus Q squared. Now, if we want to find Q that maximizes total revenue, first we have to find the critical point. And for that, I need to take the first derivative of the total revenue function and equate it to 0. So I do d by dq of TR. That's going to be 30 minus 2Q. And I will equate this to 0. And that gives me Q is equal to 15. And now the next step is to check if this Q is equal to 15 actually maximizes total revenue. And for that, we do the second derivative test, which is I take the second derivative of dr with respect to Q, which means I'm actually taking and differentiating this function with respect to Q. And what do I get? Minus 2. Minus 2 is always less than 0. So we're dealing with a concave function. Therefore, we can be confident that Q is equal to 15 maximizes dr. And if you want to find that maximal value of total revenue, how do you do it? So you just have to calculate dr at Q is equal to 15, and that will just be 30 into 15 minus 15 squared. So this will be what? 450 minus 225. So that will be about 225. So that's how you solve the first part of the question. Now let's go ahead and solve the second part, where we want to find Q that maximizes total profits. Okay, so we all know that total profits are given by total revenue minus total costs. And in economics, you'll often see this notation of profits being written as pi of x or pi of Q here. So pi here is just a notation that you'll see economists using to denote the profit function. Now let's go ahead and compute this profit function. So we have total revenue is what? 30Q minus Q squared. And we're told that the cost function is actually, I have it right here somewhere. Yeah, so the cost is half Q squared plus 6Q plus 7. So let's write down the profit function. So we have 30Q minus Q square minus half Q square minus 6Q minus 7. So combining like terms together, we have minus 3 by 2 Q square plus 24Q minus 7. So that is my profit function. Now we want to find Q that maximizes this particular function. So let's take the derivative. First derivative and equate it to 0. So I have minus 3 by 2 into 2Q plus 24 equals 0. So minus 3Q plus 24 is 0, which gives us Q is equal to 8. Now, is this the maximum? Is this Q that maximizes my profit function? Let's take the second derivative, which means I want to take the second derivative of this particular function. And that happens to be just minus 3. Minus 3 is always less than 0, telling us that Q is equal to 8 is maximizing the profit function. If you want to find the corresponding profit value, you just have to plug in 8 into this profit function, and that will give you the maximum profit. Now, the question actually also asks us to calculate MR and MC at this value of Q, and what do you see? So I've given you the total revenue and the total cost and the profit functions, and we found this Q that maximizes total profit. So this part of the question, I'm going to leave it as an exercise for you. Now, the last question, I'm just going to help you set up the different functions, and then from there on, you're going to take it forward and practice. So if the fixed costs are 15 and if the variable costs are 2Q per unit, write down the expressions for TC, AC, and MC. So I will help you write down the total cost function. So we're given that total cost is so we know that the total cost is just fixed cost plus variable costs. So fixed costs are those that do not vary with the quantity. They're just a given lump sum amount that you have to incur. Say something like the rent that you pay for the rent that you pay for an office or for a factory, and that is immaterial of the amount of goods that you produce there. So that's fixed cost. And variable cost is where the more you produce. So the variable cost is that part of your cost function which varies with the quantity that you produce. So in this particular case, fixed costs are given to be 15. So that will just be a component of my total costs. And my variable costs are 2Q per unit. So if I'm producing Q units of output, that is, if I'm writing total cost of producing Q units, my 15 here is material is independent of the amount of output that I produce, so that just goes in as it is. But I have 2Q per unit of production, and I produce Q units. So the variable costs are actually going to be 2Q squared. So this gives the total cost function be just 2Q squared plus 15. And from here on, you have to compute average cost, which is AC, and then marginal cost, which is MC. And then go ahead and solve for this particular question, what this particular question is asking you to do, which is to find the value of Q, which minimizes the average cost. And that will be an exercise for you to finish. And with that, this video comes to a close. Thank you.